The next network type that I'm going to talk about is going to be point-to-point network type. Point-to-point also uses 10 and 40 as the timers, and collectively this combination of 10 seconds for the hello timer and 40 seconds for the dead interval is something that is very, very often referred to as fast timers. Now, why fast timers? Because they are faster than the other set of timers, which we call slow timers. I'm going to talk about them in a minute. The hello type here is also multicast, and this is something, and I always have fun explaining this in the class. I ask the question usually, are we sending unicast or hello or multicast hellos on point-to-point network type? And there will always be one or two students who would say, well, we are sending unicast, it's a point-to-point link, there is no point to send multicast. Well, let's take a look at that in a case that some of you might have a confusion about it. Let's say that I have two routers. So router 1 and router 2. And let's say that they are connected on serial interface. And the IP address here is 10.51.73.85/8. And here it's 10.101.93.105/8. Are these on the same subnet? Well, the answer is yes, they are. So if I'm to send a unicast hello to this router here, I would need to know what the IP address on this side is. Now, the only way I can know the IP address of the neighbor is if I actually manually configure it with the neighbor statement. But for point-to-point network type, there is no neighbor statement in use. We don't have to configure the neighbor statement in order to use point-to-point network type. So how do routers know what the IP address on the other side is? They don't, because they don't care about it. Because the actual hello that is being sent is going to be sent to 224.0.0.5, precisely to avoid having to know what's on the other side. Because the only way we would ever know what's on the other side is if we used /31 mask. And /31 mask is not actually a requirement to get the point-to-point network type going. So this is why we are sending multicast hellos, and we don't need the neighbor statement. Because it's a point-to-point network type, we cannot have more than just two devices connected there. There is no DR and BDR election. The mask is going to be the correct mask advertised, just like for broadcast network type, and the next hop is irrelevant in this case because, again, we cannot have three routers, so there is not going to be a situation where we have hub and spoke environment with the point-to-point link. So this field does not apply to point-to-point network type. This is the default on all serial interfaces, and it's also default on all frame relay point-to-point interfaces. Technically speaking, there are some other interface types where this is the default on. So it will be on all the dialer interfaces. It would be on all virtual access interfaces that are spawned from the virtual templates. It would be the default on all ATM point-to-point sub interfaces. But you know, those are some fringe cases. So in this case, these are the ones that you actually care about for the purposes of the CCI lab. The next network type that we're going to talk about is going to be non-broadcast. Now, non-broadcast has many characteristics it shares with broadcast. The differences are that it uses the slow set of timers, so the hello timer is 30 seconds and the dead interval is 2 minutes. The hellos that are being sent are unicast hellos, which means we need to use the neighbor statement to configure our peers. There is DR and BDR election. The mask that is being advertised is the correct mask, and the next hop behavior is the exact same as it was in it's exact same as it was with the broadcast network type. Now, this is the default network type on frame relay physical interfaces. So if you are enabling OSPF on a physical interface, that means without sub interfaces, and it's also default on frame relay multi-point sub-interfaces. Okay, the next network type that we are going to cover is going to be point-to-multipoint. Now, point-to-multipoint also uses the slow set of timers. It uses multicast hellos, which means we don't need the neighbor statement, and there is no DR-BDR election. And this is one of the reasons, if you take a look at it, it looks really like a magic solution for your hub and spoke problems. Because take a look at it. We are sending multicast hellos. That means we don't have to bother configuring the neighbors, and we don't have to worry about which router is the DR in our network. But this is where things become a little bit tricky. So going back to the whiteboard, let's take a look at a hub and spoke network. So I'm going to have a network of 3 devices. So this is going to be our hub, this is going to be spoke 1, this is going to be spoke 2. Now, let's say that the subnet in use here is 192.168.123.0/24. Let's say that this is .1, that this is .2, and that this here is .3. Now, let's say here that we have another router, R4, that is connected on an unrelated subnet. So if I do show IP route on R4 here, I am not going to see this network in the routing table on this router. What I will see is 192.168.123.1/32, .2/32, and .3/32. Each of these routers advertised only its own IP address as /32, and none of them actually advertised their common subnet. This is what I meant by what is the mask advertised. So when you have point-to-multipoint network type, it will be always the host route advertised for your local IP address, but none of the routers will actually advertise the shared subnet. Again, for the purposes of the CCI lab exam, be on the lookout for this one, because if there is a requirement in the lab, make sure that all networks are advertised with their correct masks. Point-to-multipoint may not be a solution for your problems. It can also, in some sort of advanced scenarios, create a problem for you. So let me give you an example, and actually we do have this in at least one of our workbooks, and I can tell you it was a joy to write that lab. So this is going to be a slightly elaborate scenario. So I'm going to have 3 routers that are in hub and spoke. So let's say that I have R1, R2, and R3 here. So this is a serial interface, this is a serial interface, this is a serial interface. And let's say that we have R4 that is connected to both R1 and R2, and let's say that this is a fast Ethernet interface. And network here is 192.168.123.0/24. Here it's 192.168.14.0/24, and here it's 192.168.24.0/24. Now, all these are running OSPF in a single area. So let's say that this here is OSPF area 0. And here the requirement is to run point-to-multipoint. Okay, you have configured this, and this is all fine. Now, the next requirement is configure BGP peering between R1 and R2, where R1 is in AS100 and R2 is in AS200. So I need to have a peering between these directly connected interfaces when these two are in different autonomous system numbers. Now, you might be asking yourself, why would anyone do this? And that's irrelevant. This is what the lab is asking you to do. So, okay, you go on R2 and you say router BGP 200, neighbor 192.168.123.1, remote AS 100. You do the pretty much the same thing here. You say router BGP 100, and you say neighbor 192.168.123.2, remote AS 200. And what happens is this neighbor here goes active. This session here goes active, but they never establish. It never works. And you can wait for as much as you want. This session will not establish. Now, why not? Well, we have to take a look what is happening in our network. This here is a directly connected /24 route. But the path that R2 will take to actually reach this interface here will be this. Because if this is a serial interface, the cost on this interface is 64. The default cost here is 1. The default cost here is 1. And remember, R1 will be advertising /32 here. And /32 will always trump /24. A more specific route always wins. So the actual path of the packets from here to here will go around this way, which means that not only I need to configure eBGP multi-hop, I actually need to specify that this is the source interface, because if I don't specify it, these will be the source interfaces of my BGP peering by default. And only because I used point-to-multipoint network type here. So if I use the broadcast network type here, for example, this would have not been a problem. So you see, point-to-multipoint can actually be a pain. Now, this may make you think, okay, I should maybe better just stay away from point-to-multipoint because it obviously creates a problem. Well, let me give you another example. So you have R1, R2, R3, again, hub and spoke. And let's say that this here is an MPLS PE device, and this is MPLS PE device. And here, inside VRF, we have some customer edge devices. And basically, R1 here is MPLS P device. So what we want to do is get the traffic from CE1 over our MPLS network over to CE2. Now, if you use a broadcast network type for this hub and spoke setup here to avoid the problem that I was explaining, remember that R1 and R3, let's say that this is R1, that this is R2 here, and that this is R3, just to make it easier. So R1 and R2 here need to communicate, right? And we need to reach the loopbacks of these interfaces to get our MPLS working, to get the BGP, the multi-protocol BGP. I will talk about it later on. But the problem here is that when R2 looks at its routing table, if this was a broadcast network type, what would be the next hop of loopback of R1? It will actually be R1 itself, which means that the traffic that gets sent to R3, MPLS traffic, will be sent with the wrong label. It will be sent unlabeled because R2 will not have labels from R1. Why? Because there is no direct communication between them. They cannot exchange the labels. What we need to do is we somehow need to send the traffic for R1 to R3, telling R3 that this is the traffic that needs to be sent to R1 using a label. Now, to do that, we need to use we need to use point-to-multipoint network type, because in point-to-multipoint network type, the next hop will actually change, and this will solve this problem for us. So, getting rid of MPLS for a moment, if we have hub and spoke setup, so this is spoke 1, spoke 2, and this is hub, and we have our network N. If this was a point-to-multipoint network type, when this route N gets advertised to hub, and hub sends it to our spoke 2, we are going to have network N that is reachable through hub. So the next hop will actually be this interface, not this interface as it was with the broadcast network type. So in this case, we are changing that behavior. So you see, it's not necessarily that the broadcast network type is bad or that our point-to-multipoint network type is bad. They both have their good sides and they both have their bad sides. It is up to you sometimes in the lab to make a decision, which is the network type that you want to go with. And this is where understanding the big picture of how one technology can influence another technology. In this previous example, I've given you an example where choosing a network type broadcast here can cause you the problems with MPLS. In this case, I've shown you an example when choosing point-to-multipoint network type can cause you the problems with BGP peering. Now, in both cases, the situation is solvable, it's doable, it just becomes a little bit more difficult. So you are often going to be in a situation that you have to choose between two evils. Are you going to go with a relatively easy OSPF and then have more complicated BGP, which is this example, or are you going to go with slightly more complicated BGP in case that this was the same scenario like the one before? Are you going to go with slightly more complicated BGP but not overcomplicate MPLS? There is actually a solution for this with broadcast network type, but it's a little bit outside the scope of what you will ever need to know for your CCIE RNS. So going back to our table here, point-to-multipoint is not the default on any network types, so I'm just going to leave it as empty. The question that I had here is, couldn't I just add frame map IP of the loopback address to map it to a hub site to solve, I suppose, this problem with MPLS? Well, no, because that would just tell R2 that if it wants to send traffic for this destination, it needs to send it out of this interface. But what we need to tell it is to send it with the correct label that R3 gave us in the case of MPLS. So if we send the traffic, it doesn't matter how we send it. We can use policy routes to force the traffic there. But the point is that we need to tell the control plane, you need to send this traffic with the label that R3 has given you. If that doesn't happen, R3 will get the packet that is marked with the wrong label that it probably doesn't understand, and it's going to drop the traffic. Or it can get unlabeled traffic and drops it again. So, as I said, this is a relatively advanced scenario. I need to first explain MPLS in some great detail so that you can understand. Next network type that we're going to go through is going to be point-to-multipoint. Point-to-multipoint. Non-broadcast. Now, as the words imply, this is going to be very, very similar to point-to-multipoint. The timers are going to be the slow timers. Because it's non-broadcast, we are going to be sending unicast hellos, which means we need a neighbor statement. There is no DR, BDR election. /32 gets advertised. The next hop is the hub, which means it gets changed when advertised, and this is not the default on any of the interface types. So as you can see, very, very easy and straightforward. Last but not the least is going to be the loopback network type. The loopback network type is the default on all of the loopback interfaces, and it's important to explain it and treat it slightly differently than other network types because of the special behavior it has. There are no timers because there are no hellos being sent. You don't need the neighbor statements. There is no DR, BDR election. But no matter what you have configured on an interface, /32 will be advertised. And of course, there is no next hop because you cannot have any devices connected to the loopback interface. So these are the OSPF network types. Now, I should say that these are the OSPF network types from the perspective of the interface configuration, and the behavior when it comes to adjacency forming. In the database, in the OSPF database, the story is very different. In the OSPF database, you are only going to see 3 network types. They are going to be stub network type, point-to-point, and a transit link. I will talk about those a little bit later on.